we have previously covered the topic of continuous outcome, and then we talked about what are the things that we need to do when we have binary outcome. And before that, we covered the topic of why do we need to do prediction. Prediction is basically to predict something based on some future data, and we are basing that prediction based on what happened in the past, right? And if we are basing our prediction based on past, and then we are doing our prediction using that same past data, one of the problems that we know that happens all the time is that there is a overfitting or optimism problem where you are getting overly optimistic results in your prediction problem. But using the same data to build the model and using the same data to make the prediction is not really the purpose of prediction. The purpose of prediction is always to generalize, to work on a different data, new data, external data, and all that. So if we are building the model and making the prediction using the same data, that is kind of defeating our purpose already. And since we are getting lower results of the prediction error measures when we are using new data, we obviously want to protect against that type of problem. And there are a couple of ways to protect us from overfitting problem. And one of those ways we have learned is the split sample situation, by which we split the sample into the test sample and the training sample. And a generalization of that split sampling idea is the cross-validation idea. In that cross-validation idea, we have seen that we just do the same thing iteratively in a way that our test data and training data are not really the same within that cross-validation. And eventually what we do is that within cross-validation, within each training data, we feed the model, and then we test use the test data to obtain the prediction error. And then we do it for all of the cross-validation folds, and then we simply average out all of the R-square or ROC, whatever we get, to get the overall understanding of what is going to be our prediction error. Okay, then we started with an example of a linear regression. Then for binary outcome, we talked about logistic regression. And then we talked about one small problem of if we wanted to do variable selection, and we do not necessarily want to just use all of the variables all the time, we could use the variable selection within the logistic regression model, specifying some of the parameters, such as here, I'm specifying the GLM step AIC, and I'm saying the direction, like start with the full model and then start deleting variables that are not necessary anymore. And the purpose of this exercise is not to find a smaller model. The purpose of this exercise is that even if you make your model smaller, does it help increasing your AUC or the ROC from ROC that you are calculating? And we have seen in that particular example, the ROC values are not very different compared to the regular logistic regression when we have fit. So this variable selection exercise did not really help in our situation. Okay. So then we started our supervised learning chapter. And in this chapter, we again started with the same data set and this RHC analytic data set that we have saved previously. And then we started talking about our first machine learning method. And this first machine learning method is generally known as the regularized method. Why it is regularized method? Because the only thing that it is doing on top of what our regular regression does is that it is adding a penalty term. So for ridge regression, this is very similar to what we have seen in the regular regression, and this is also very similar to what we have seen in the regular regression. The only difference is in here we have a lambda sum of beta square, and in here when we are talking about lasso, we have a lambda absolute of beta terms. Right? So this is the only difference. Here I have the square term and here I have the absolute term. And the implication of this is that the ridge regression, what it does after adding this penalty is that it does not let any coefficient go close to zero. If it is close to zero, it will just push it back so that it's not close to zero anymore. And lasso does the completely opposite thing. If some coefficient is close to zero, it will just give it a small push to make it zero so that that variable is completely dropped from the regression. And eventually what will happen is that in the lasso, you will have less number of covariates, whereas in the ridge, you will still have all of the covariates that you have started with. Elastic net is a compromise between these two. Say, for example, you have 50 covariates, and in a regression, when you fit, you will still have 50 covariates. In ridge, you will still have 50 covariates. In lasso, it might be 10 covariates after doing all of this deletion of parameters. And elastic net is somewhere in between. It will be somewhere between 10 and 50, right? So this is a less aggressive version of lasso. And sometimes people like elastic net method because lasso, what it does is that, say, for example, you have a group of covariates that are correlated. And what lasso will do that, say, for example, within the group of 5 covariates, it will try to pick just one, and then it will delete all of the rest. So this is a very aggressive method, this lasso method. Elastic net method will not do that. Elastic net method will still try to figure out whether there are other variables that are maybe correlated, but can we still keep them in our model? So this is a reasonable compromise, I would say. Okay. So now that we kind of understand what these regularized methods are doing, we are trying to fit, say, for example, at first, how to fit the lasso model. And in here, what we are doing is that we are just specifying our alpha has to be 1 and lambda is some specific value 0. We do not really care too much about lambda because eventually within GLMNet, there is a cross-validation step that it does internally. That is not the same cross-validation that we do. It does internally a cross-validation to figure out what is the best optimum value for lambda. So we do not really need to specify lambda. All we really need to specify is the alpha value. And alpha value is the mixing parameter that will determine whether this is a ridge regression or a lasso regression. And just to remind you, this is the lasso regression where we are having this absolute term, right? So when you set alpha equal to 1, that will choose that absolute term. And after that, we estimated the root mean squared error. Remember that this particular example that I'm using, this is an example of a continuous outcome. That is why it is calculating me these root MSC and the R squared values. We could also try to calculate the ridge regression, and the way to do it would be simply to change your alpha value from 1 to 0, and it will automatically calculate your ridge regression. And from that ridge regression, you can still see the RMSE and R square values are not very different than what we have seen for the lasso values, right? Okay, so let us move on to the binary example. In the binary example, compared to the continuous example, if you look very carefully, you will see there is a difference between how we select our options for the train control function. The function, in that function, we're simply saying we need a 5-fold cross-validation. We do not say anything else, right? And this is happening for the continuous outcome. For the binary outcome, what we are doing, we are saying that we need to have the estimation of the class probabilities, and we need the summary function of that class probabilities. The reason we need that, because we are now dealing with a binary outcome, and the binary outcomes, the way we make the predictions is that we make the, instead of making the mean of the outcome, now we are talking about the probability of the outcome. What is the probability that you will be dead versus what is the probability that you will not be dead? And that is why we need to add these additional arguments in the train control function. Okay, and all of these things are exactly the same as we have done in the continuous outcome, except for the metric. In here, we do need to specify which metric that we want to estimate. If we do not mention this metric, it will give you some sort of sensitivity and specificity values that we are not really using in this particular course. We are basically using the AUC from the ROC curve. And when you do that, the ROC curve gives you, there is a labeling issue within the caret package. It says that this is ROC, but this is basically AUC value that is coming from the ROC value. AUC means that area under the curve, and this is the receiver operating characteristic curve based on which we are calculating this AUC value. And you see that ROC or the AUC value that we are getting is 0.754. Knowing that the range between the possible ranges for AUC is 0.05 to 0.5 to 1, and this is somewhere in between. So we know that this is somewhat okay value. It's not like a useless value that we have seen in our continuous outcome scenario, right? Okay. In the same way, we are still on the binary outcome. We could still do the ridge regression. The only thing we would need to change is we would change the alpha value from 1 to 0. And that would give us the value that we want. Okay, I want to talk about elastic net for a second. In this elastic net scenario, what we are doing is that instead of setting the value of alpha to either 0 or 1, we are saying we do not know. We can say that maybe it belongs to some particular alpha value. These are the possible ranges, but I do not know what is the best possible alpha values. Then you can specify your alpha values and ask caret to find out the best possible alpha value that it can get based on the best AUC or ROC value that it is calculating. Not only that, you can also specify the lambda value, that is the regularization parameter value, that lambda in the equation that you have seen. You can also specify and ask caret to check which lambda value is good enough for our scenario. What caret will do eventually, based on this grid of parameters that you have supplied, these alpha values and these lambda values, it will calculate all possible ROC values that can be calculated. And then based on this table, it will try to identify which is the maximum ROC, which parameters are associated with the maximum ROC value. And it will report it at the end. So it says that the final value of the alpha value that was best was alpha equals 0.01 and lambda that was best was 0.05. So the minimal value that was given, that was the best possible value for the ROC, right? And you can obviously try to plot it and try to see how did the ROC decreased when you are choosing the mixing parameters and regularization parameters different, right? Any questions so far? Yes.
For the alpha value, is it just between 0 and 1?
It is between 0
It has to be between those two.
Yeah. Any other question? Okay. So now we are going to move on to a slightly different type of machine learning method. Regularization methods are very good at stabilizing your regression. For some reason, if you have a suspicion that your regression is very unstable, by unstable, I mean that in different folds, it is giving you wildly different results. Usually, these shrinkage methods or the lasso regression and elastic net methods are very good at stabilizing your regression. One of the advantages of lasso or elastic net method is that it is designed to handle multicollinearity issue. So if you are dealing with variables that are highly correlated with each other, lasso method is your go-to method. Also, in certain scenarios, for example, when you are dealing with medical data sets, you will see in many of the situations you will have lots of zeros and very few ones type of scenario. In those type of scenario, what we call them is sparse data situation, where you have the dominance of one particular value in the data set, and your lasso method is also very good in handling those kind of sparse type of scenario. Okay. Now, the second type of method we are talking about. So the first type of method was very helpful in identifying important variables, right? The second type of method we are talking about is the decision tree method, and these decision tree methods are basically very helpful in identifying the functional form, right? And what do I mean by the functional form? The functional form means whatever is in your right-hand side equation in your regression. In your right-hand side of your equation, you simply generally mention what are the main effect terms, right? And in the main effect terms, we generally have to specify which interaction term we want, which polynomial terms we want. But for the decision tree, what it does is that as long as you mention all of the main effect terms, it will automatically determine what interaction terms are needed, what polynomial terms are needed, what are the complex functional form are needed. It will create that complex function for you. So you do not need to worry about any of that. So this is the main advantage of decision tree. So it is able to find out the best possible functional form. The problem with this method is that this method is highly unstable. So as you have seen in the previous class that I was talking about, a tree that is growing, and if you can imagine that if you have a lot of covariates, or if you are dealing with continuous covariates, the tree can grow very fast, and it can be a unmanageable tree very quickly. It's like some sort of herb that you grow in your garden. Sometimes it goes up. You cannot even control it. So trees like that. Sometimes you do not even know how to control it. And obviously, because this is an unstable method, there is a huge problem of overfitting for this decision tree. So obviously, we definitely want to do some sort of cross-validation to address this overfitting problem, right? And to do cross-validation, we simply go through the same process of using the train control function to specify the cross-validation and which number of folds. And since we are dealing with a binary outcome, we still need to specify the class probability and the summary. Then all we need to do is to specify which method we are going to use. So for the tree method, a basic type of tree method, we want to use the rpart package. The thing is, tree methods are known as the classification and regression tree. And the people who invented this method, they copyrighted the name. So when the people who were in R, they were trying to write a package in cart and name it cart, they were not able to make it because this was a copyrighted name. So they named it rpart, right? Anyway, so when you want to calculate the basic cart model within the cross validation, this is the way you do it. Within the train, you just mention the method equals to rpart, and that will give you the estimates. And you can see there are some CP parameter that it is trying to also see which CP method is the best. This is just a parameter that this cart method uses. Basically, we're interested in this ROC estimates, and you see the best estimate is this one. So you would pick that one, right? But remember, when you were doing the lasso method, you were getting your ROC or AUC very close to 0.75, but this is like 0.63, right? Because it has this overfitting problem. And when the overfitting problem is happening, and all of these numbers, the ROC numbers that you are seeing here, are coming from the test sample, right? And obviously, you can see from this example that there is this overfitting problem that even after cross-validation, you are not able to get rid of completely. Okay, so as a solution to that problem, because we love all of this characteristic of this cart method, because like it can automatically determine the functional form and all that, but it is very unstable. So what is the solution? One solution they came up with is that forget about cross-validation. Think about the basic type of cart method. What if we just resample the data 1,000 times, and in each of this in each of this 1,000 resampled data, if we fitted the cart method every time, what is the ultimate ROC that we would get when you averaged out all of this? So that is basically the bagging method. So what this bagging method is doing is that instead of fitting it one time, it is fitting it, say, for example, 1,000 times, but the data is not exactly the same every time. The way they are doing it, they are just resampling the data with replacement. That means that one particular person could be chosen multiple times in the data, and they are doing it. So every time the data size will be similar. So if you are dealing with a 5,000 sample, every time you are resampling, you will get another 5,000 data set with 5,000 people. Maybe not some of the people are maybe not some of them are not unique. So some of them are counted multiple times. Some of them are not even included in the sample, but the sample size will be same. And then you just take the cart method and apply in that data, and then you try to figure out like whether the method is stable enough or not. And on top of that, you can still do cross validation, right? So it is doing it, like it is using a lot of computing power actually. So when you are specifying bag, it is already doing the resampling 1000 times, and now you are doing the cross validation. So like you are doing it like 5000 times or something like that, right? So it is using a lot of computing power. And of course, there are some additional parameters that you need to specify, but these are some of the default parameters. You do not need to specify anything extra. And this train control is basically the same. And once you do it and you get the ROC, see, the ROC is back to 0.75 level for this bagging method. And one of the useful features of this bagging method is that bagging method can actually give you the most important covariates. So it can tell you which covariates are most important in predicting your outcome. So in here, and this is ranked by the way, so you can see the age variable is the most important, then the Apache score is the second next, then the DAS index in the third next, and stuff like that. Okay, so that was the bagging method. Any question about the bagging method so far? No? Okay. Yes.
The number of sampling times is not arbitrarily defined 1000 that's a fixed.
It's just some number that is large.
Okay.
So it doesn't have to be 1000. If you want more stability, you you just have more samples here. Okay, so boosting method is very similar to bagging method, but the only difference is that in the bagging method, all of these sampling are happening independently. There is no relationship between one sample to the another sample, right? But boosting method is slightly different in the sense that whatever you are learning from your first fit, you are probably better off using that information when you are fitting the second model. So it is just using the information sequentially to update the fitting process. And this process is known as the boosting process. And in the R, there is a package called GBM package, and that fits your boosting model automatically. And after all of this, you get, so which was the best parameter? It was the 150 interaction depth. Equal to 3 shrinkage, and okay, so this is the best possible value, I think, or this one. This one is the best possible value that you can get out of a boosting method, and you can see this is not as good as the other methods. Other methods were giving you 0.75, and this is giving you 0.74. So that is what it is, and you can still see how the different type of parameters are changing your ROC. Okay. There are some other machine ensemble methods. So these ensemble methods, bagging and boosting that I talked about, are basically using the same data. It's just resampling those data sets, right? And we are using. Okay, let me clarify that point. So what I'm doing here is that I'm resampling those data, but I'm using the same models every time. So like I'm using cart. So I'm not using any other models, right? But it is possible that you change your models every time. So you can fit cart, lasso, other machine learning method, and so on. So you can try to change it in the data. And you do not resample in that case. You are just using the fixed data set that you have, and you are just using different type of models. And that is something that is called super learner. I am not going to cover that method in this class particularly, but I think that you generally understand the situation that you are simply using the same data, but you are basically using different models in this. And there is a package called super learner within R that can automatically do the super learner fitting within your data.